Your class starts at 4?
Yeah.
Then real quick, I can talk to you about it.
I wasn't able to show up for the meeting on Tuesday. So I was very easy to be effective and just went home and I talked to you and I don't know if you're gonna talk about the things that's the last session and also be lost.
I mean, I'll do a little bit of review from last time, so I think it wouldn't be bad to sit here while you're here. But definitely go watch the recording afterwards and stuff.
Okay. Yeah. And also, it's kind of like just the other countries, you know, I haven't started on the picture project. I did look at it again to see what I need. I just wanted to check in with you for this speaker. All I really need to do is just take one of the things, do 3 different tests, when you read a review button, or not review a pacer button.
Yeah, that's basically it. But yeah, you need to be. But the report that you're writing for it's going to be a lot more detailed than the activity reports that we've done so far. And so I really want you to explain in detail, you know, the mesh that you're choosing, kind of why you chose the settings that you did, boundary conditions that you chose, why you think those are realistic. You know, I want you to write a little background information, introduction. So a lot of the work in the project is actually going to be the report. Most of the simulations you can knock out and that can happen. You know, those are pretty fast. And so
that's what I was thinking. And real quick, because like this is like the first thing that came to mind in terms of what I would be doing. And I just want to provide value and like some tools for what we want. How getting the part of the ID and just doing a test on to see which if it would be stronger in the compression or intention.
Well, it's going to be exactly the same because we're assuming a linear elastic material, so you're not going to see any differences in tension and compression. And so you can do one of those to one of your conditions, but the plot is going to look exactly the same. You're going to have the same deformation, right? It's going to be in the opposite direction, and the stresses are going to be identical. So that could be one of your conditions, but then the other two, which things? Thank you. Yeah. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good. So hopefully, some some of you I know went to the career fair today. So hopefully that went well. Okay. So today we're going to continue where we left off on Tuesday. So on Tuesday we were talking about quadratic interpolation. I believe we kind of left off right in the middle of an example, so we'll kind of pick that up. We'll finish that up there, and then we'll move on to the last topic in the set of lecture notes, which is direct root methods. Okay. And so all of these are kind of all very viable and very good ways to solve 1D problems using a nonlinear approach. Okay. All right. And so some announcements. So homework 4 is out there right now, and so hopefully you guys have had a chance to take a look. That's going to be due at the end of next week. So definitely check that out if you haven't had a chance to look at it. Okay. Another announcement I want to make is I brought the midterms with me today. So if you are here in person, you can pick up your midterms. So I got a chance to grade all of them. So the midterm average is about 40 out of 50. So you guys did really well on the exam. And so I was really happy with how you guys did. And most of the mistakes that I saw were not really you guys knew what you were doing, and I think that's kind of what made me happy the most. It was just mostly like mathematical. So I know a lot of the algebra, especially the foiling, got to be a lot. And so I think I saw most of the mistakes were there more so than you guys not really knowing what to do. So that's a lot more forgivable than that's really good. Okay. Another announcement that I have to make is that I'm working on the final project for the class, and so I was able to make a lot of good progress on that the last couple of days. And so I think I'll have it ready to present to you guys either end of next week or early the following week. Usually, for my class, I like to kind of present the final project around week 10, week 11, just so that you have a little bit over a month and a half to work on it before it's due middle of December. Okay. So definitely keep that in mind and I look forward to that over the next couple weeks. All right, so that's all my announcements. Are there any questions I can answer before we get started for today? Okay, all right, so let's go and get started. So actually, first thing I'm going to do, I'm going to scroll up here a little bit. So I'm going to kind of go back to the last example. Okay. And so this is the example that we were doing kind of right before we left off on Tuesday. And so on Tuesday, we're looking at this objective function here. We have f of x is equal to x raised to the 5th power minus 5x cubed minus 20x plus 5. And we want to find the minimum of this function using quadratic interpolation. Right? In other words, we're basically going to take this function, we're going to replace it instead with a quadratic function and then find the minimum of that quadratic function. Okay? That's the whole idea with quadratic interpolation. Is that you take whatever objective function you can have any form in the world, it can be almost anything, and instead of minimizing that function, we're minimizing a quadratic function because that's a lot easier to do. Okay. Okay. So the first step in this procedure was to find an appropriate step length. Okay. And that's that's basically mostly just to get our first 3 initial points. Okay. And so we were told in the problem to start with a step length of 0.5. And then using that, we could see, we wanted to see if we could actually build a good quadratic surrogate function. Okay. Because if you recall, based on our initial 3 points, we can build different kinds of surrogate functions, and we want a situation to be like this, where the first point that we select is at some midpoint value. The second point, which is 1 step length away at B, that should be the minimum. And then when we come back up for FC, which is 2 step lengths away, we should come back up. Okay. And so we want to make sure we choose our step length so that we get this situation right. Okay. And so we basically just kind of did trial and error here. So we tried with a step length of 0.5, and we made our 3 function evaluations here. So we made FA, which is at f of 0, FB, which is at f of 0.5, so that's 1 step length away. And then we did f of 1, which was 2 step lengths. Okay, and we got their values, and we found that each of them are all increased. So we have 5 minus 5.6 minus 9. Okay, So what we found was that based on these values here, the fact that FC is the smallest, FP is the second smallest, and FA is the biggest, right? We need to make our step size bigger. Okay. And that's what we set out to do. So after we found out that we had to make our step size bigger, we doubled it. And so we went to t is equal to 1.0. Okay. And then we evaluated our objective function at those three locations. And what we found was that, you know, we're still kind of in the same situation here, where our function is still decreasing as we go through each of those points. And so once again, we have to make our step size bigger. And so we do that one more time. And so we try a step length of 2.0. And what we found was that f of 4 is 629. So FC here is greater than FB. Okay. This 629 is greater than this negative 43. Okay, so that's basically the criteria that we want to have in order to, you know, get our result the way we want it to. And so now we can go ahead and proceed. So now that we know that, you know, our step length needs to be 2.0, we can then move on to the next step in the algorithm. Okay. But the question I kind of posed to you guys kind of before we left on Tuesday was that, okay, you know, now that we have this step length here and we're able to get a surrogate function where the minimum is going to be somewhere within that range from 0 to 2t, okay? So we've established that. But, you know, if we do this, you know, is the surrogate function that we're going to get actually a good representation of our original function? Okay? Because, you know, it's very easy to kind of draw a function here that has the same minimum, or has a minimum in the same area, but that doesn't mean that it's a good representation of our original function. And so, for example, let me kind of show you. So these are bad surrogate functions. Right. So we have a surrogate function. So let's say that, you know, we defined our step size so that it looks like this. Okay. So in black right here, I have a surrogate function, which remember is our quadratic function. And so our underlying original objective function may have a minimum here as well, you know, but it may be something like this. And so it's true that, you know, this original function, it has a minimum in this range. It's just that it's kind of far off, right? Because if you look at the location of this minimum, the location of this minimum is about there. But then the minimum of our surrogate function is around here. Okay, this is our original minimum. This right here is our surrogate. These are quite far. Okay. Ideally, we would want to define our surrogate function in a way where these two are matched. Okay, so they're basically in common. Okay. Okay. And so that kind of begs the question of, you know, how do we actually evaluate, or how do we actually test to see whether our surrogate function is a good approximation of our original function? Because for a situation like I've drawn there, like, we could visualize that, we can kind of see that the minimum of our surrogate function is quite far off from where we need to be, okay? But there's also kind of a quantitative way, to compute this as well. And so we can compute something like this, so. Let's compute this quantity. And so basically we're going to evaluate the function at the surrogate minimum. So let's assume x min is determined from the surrogate. Remember the formula for x min here is minus b over 2c, okay? Remember our surrogate function h of x looks like the following. We have a plus bx plus cx squared, okay? All right. And so if we evaluate the following quantity, so let's take h of x min, and so we're going to evaluate the surrogate function at its minimum, okay, minus f of x min. Okay. So this f of x min, that's our original objective function evaluated at the surrogate minimum, okay? Because right now we don't know where the minimum of the original function is. Otherwise, we wouldn't be going through this exercise. Divide this whole thing. We're going to normalize it. We're going to divide the whole thing by f of x min as well. Okay. Just to make sure that we're positive, we're going to take absolute value of this entire quantity. And then what we're going to see is that if this is less than some threshold, it's right here, it is on accuracy failure. Okay. So a little messy there just because I was writing notes on the side, but that's essentially what we're going to do. Okay. So ideally, if our surrogate function is a good representation of our original function, that quantity in the absolute value should be around 0, right? Because what that would tell us is that what we're obtaining from the surrogate function is basically the same thing as our original function, and then the numerator of that fraction will become 0. Okay. It may not be exactly 0, and in fact, it's really hard to get this to be exactly 0, just because a lot of times your surrogate function is going to have a different mathematical form than your original function. Okay, and so just in the example that we're doing, our original function was a 5th order polynomial, but our surrogate function is only a 2nd order polynomial. It's only a quadratic. Okay. And so that means usually for this accuracy threshold, we usually choose some small number. And And so we choose a number, what did I choose for this one? I think I chose 0.1. But of course, if you want a more accurate surrogate model, if you want a better estimation, you can choose a lower value for the accuracy threshold. You can choose 0.01 or 0.001. But usually 0.1 is a decent, it's a decent starting point. It kind of saves you some work on iterating. Okay. So let's test this on our current example. And so if we test this on our current example, well, actually didn't even write down the surrogate. So let me kind of scroll back up here to see. Okay. And so for our current example, we have the following F values. Okay. So let me go ahead and bring those down here. So for the current example, we have FA. FA is equal to 5. Okay. FB. FB was at f of 2, which is minus 43. And then FC, which is our original objective function evaluated at x is equal to 4, is equal to 629. Okay. Okay. So let's use these to compute the coefficients of our survey. And so our three coefficients here are A, B, and C. Okay. So A, the formula for A is very simple. It's just FA. For B, it's 4 FB minus 3 FA minus FC divided by 2T. Okay. And then for C, what we have is FC plus FA minus 2 FB, and it's all divided by 2T squared. Okay. So those are formulas we went over last week. So you should have those in your notes from. Okay, and so plugging in the numbers here, and so we have everything we need to compute these. So our A, of course, is equal to 5. Our B in this case is equal to minus 204, and our value for C in this case is 9. So therefore, our surrogate function h of x is equal to A plus bx plus cx squared. We plug in the values for A, B, and C, and what we get is 5 minus 204x plus 90x squared. Okay. So this function right here is our quadratic representation or quadratic approximation of our objective function within the range of 0 to 4. And so remember, it's not exactly the same as our original objective function, but what we're hoping is that this is a good enough approximation. Okay. Okay. So let's go ahead and compute x min. Okay. And so the minimum of this quadratic function is minus b over 2c. Okay. And so we plug in the numbers for this. B is minus 204, and C is 90. So we have 204 divided by 180, and that gives us 1.135. So this 1.135, this is the minimum of the surrogate function. So that result, the minimum of the surrogate function we found just by classical methods, right? So for a quadratic function, it's pretty straightforward. And so if you take the derivative, first derivative of our surrogate function, you set it equal to 0, you solve for x, that's exactly what you get. Okay. Now let's take this and evaluate two functions at this location. So evaluate h of x or h of x min. And so we're going to take our surrogate function and evaluate it at its minimum. And then we're going to take our original objective function and then evaluate it there as. Okay. And so if we do that, you can plug it in. So h of x min, you plug in 1.135 into this function up here, this quadratic function. What we get is minus 110.9. Okay. And the next thing, we're going to evaluate our original objective function. So that was the 5th order polynomial that we started with at the very beginning of this example. Okay. And what we get from that is f of x min, which is minus 23.13. Okay, so you can see, so you kind of see right away that this, what we got from the surrogate function at this location versus the original objective function, they're pretty far off, right? So we have minus 110 on one side, and we have minus 23 on the other. So these are not even close to each other. So this kind of already tells us that our surrogate function is not adequate. We need to refine it. But we'll go ahead and we'll run through the whole process just so that you can kind of see all the calculations. So we need to refine our surrogate. But to confirm this, let's go ahead and compute that the quantity that I had above. So let's take h of x min minus f of x min divided by f of x min has to be less than or equal to epsilon, where epsilon we're taking to be about, for this problem, we're taking to be 0.1. So a fairly loose tolerance. But even with that, we're still not going to be. Okay. And so we can go ahead and plug in things on the left-hand side. And so on the left-hand side here, we can plug in for h min. So h min we know is minus 110.9. F of x min is minus 23. And we have the same thing on the here, minus 23.13. Okay. And we're waiting for the egg package. Okay. It's amazing. It stopped right in the middle of me writing it. Right. So while we're waiting for that, if you actually plug that into your calculator, what you get in the for the quantity that's in the absolute values there is 3.8. Okay. In other words, almost a 400% error in our surrogate approximation. Okay. There we go. Now it's catching. Okay, and so since 3.8 is not less than 0.1, that means we can't be satisfied yet. And so what that tells us that our guess right now, or our approximation for the minimum of the function is not adequate. And so we need to refine our circuit. All right. Any questions on this so far? Okay. All right, so let's talk about, how do we actually refine our circuit? Okay. And so we want our surrogate function to be a better representation of our original objective function. And so what that basically means is that we want to come up with improved guesses for its coefficients, okay, A, B, and C. So if you recall, the way that we obtained these values for A, B, and C was that we evaluated the original objective function at 3 locations, okay? And then we used those 3 locations to come up with a system of equations for A, B, and C. And so those 3 locations, at least for right now, are the following. X is equal to 0. We have X is equal to T. Okay. Remember, T is our set point. And then we have X is equal to 2T. Okay. And so based on those function evaluations, we were able to determine A, B, and C. Okay. And so when we say that we want to improve our surrogate, what we're basically going to do is we're going to take these 3 locations and swap them out, or maybe move them around in a certain way that gives us a better approximation. Because right now, what we have right now is not adequate. It's not going to give us a good answer. All right. So we actually have one more location that we evaluated, but we didn't do it to form the surrogate. We kind of did it as part of the normal kind of algorithm. Okay. And so because usually if you get to this point, if you get to the point where you want to refine a surrogate, you've already kind of found out that your surrogate kind of sucks. Right? And remember, the way that we did that was we evaluated this guy right here in the absolute value. Okay. If you'll notice, we have one more function evaluation here that we didn't have before, which was f of x min. Okay. And so, the logic behind, refining the surrogate is that, can we use this point right here? Can we use this function evaluation to improve our surrogate? Okay. Because in theory, that location there, that x min, will be in a better spot than either 0t or 2t. Okay. And so in fact, that's exactly what we're going to do. But the rules for this are a little bit complicated. So you have 4 different basic possibilities based on the relative values of x min relative to the step size, and based on the relative value of the evaluation relative to f and b. Okay. So let's go ahead and list out those 4 cases. Okay. So case 1. So case 1 is going to be the case when x min is greater than t and f of x min is less than f b. Okay. Well, remember, FB was the original kind of evaluation of the objective function at the step point at t. Okay. And so in this situation, we're gonna kind of swap things around. Okay. And so I'm gonna have 2 columns here. So basically, the way that this is going to work, we're going to come up with new values for FA, FB, and FC. Okay. Because remember, we use those FA, FB, FC to compute, A, B, and C. And so the new value for FA is going to be set to the old value for FB. Okay, so you're going to take your old value for FB, set it to FA. Your new value for FB is going to be F of X min. And then your FC stays the same. Okay. And so this also implies that the new value for XA is going to be the old value for XB. Okay. The new value for XB is going to be X min. And XC in this case stays the same. You do a little bit of a switcheroo. So, and so what this means is that the odd person out here is the old FA. Okay? So we're going to discard old F, which was the old F of 0. Well, that's the first case. Second case is if x min is greater than xt, or greater than t, I should say, and f of x min is less than f b. Okay, well, that's the same thing. Greater than f. Okay, and so in this case, we're going to perform another switcheroo. And so I'm going to use the same format as before. So the first column is going to be the new values, and the second column is going to be the old values. And so in this case, FA is going to stay the same, FB is going to stay the same, and we're actually going to throw out FC. So the new FC is going to be F of XB. And of course, this implies that XA is still XA, XB is still XB, XC is X min. Okay. So that's the second case. Let's do the third case now. So third case is if X min is less than T and f of X min is less than F. So in this case, we have FA is still going to be the same. FA is going to be FA. FB here is going to be set to f of X min. And then the new FC is going to be set to the old FB. XA, XA, XB, equal to X min, and then XC is equal, the new XC is equal to the old XB. I know this is painful. It's painful for me too. There's so many weird rules, and that's unfortunately just a lot of what these algorithms are. It's just lots of kind of weird rules and kind of edge cases, and you have to kind of follow the logical steps. And so so this is not something I expect you to memorize at all. And so even I don't have this memorized. So I'm writing this down just so that you'll have it in your notes, and so you can refer to it. And so when you're doing problems, you can refer to this table to kind of know exactly what you need. Okay, so there's one more case. And so if X min is less than T and f of X min is greater than F. All right, and so in this case, FA is equal to f of X min. Okay, so we're going to discard the old FA here. FB is equal to FB, and FC is equal to FC. Okay, B and C stay the same in this case. A min and then XB stays the same and XC stays the same. Okay. Honestly, this is way too much writing for what this actually is. So, so basically, what we're going to do is we're going to go back to the example and then see which of these rules qualify for that, and then refine our surrogate model. Okay. All right. Any questions on this? Okay. All right, so let's go ahead. Let's go back to the example and then see which case we can use here to improve our survey. And so if you recall from the example, let me go ahead and write out all the relevant information here. So in the example, what we found was that X min was equal to 1.135. Our value for T in this case right now is 2.0. F of X min is equal to minus 23.13. And then FB was equal to minus 40. So those were kind of that's kind of the status of our problem, kind of when we looked at that. Okay. And so based on this, we can see that our guess right now for x min is certainly less than t, right? Because 1.135 is less than 2.0. But also that we see is that f of x min is actually greater than fb. So let's see which case this corresponds to back in the document. Okay, we have x min less than t, and so that's going to be either situation 3 or 4. Okay, and since f of x min is greater than fb, this is situation 4. The case 4. Let's go ahead and make the relevant substitution. So we have fa, the new fa is equal to f of x min. So that's going to be updated to a new value, and so fa now is going to be minus 23.13. FB is going to stay the same, so FB is still going to be minus 43. It's the same. FC is going to be same, which is 600. And similarly, we need to update the values for x. Okay, and so for XA here is going to be updated, so we're going to set this to be x min, so this is 1.135. Our value for XB is 2.0, so this is going to stay the same. Our value for XC is 4.0, which again is going to be the same as before. Okay. Okay. So that's good. So now we can use these values here to update our surrogate to get new values for A, B, and C. Right. And so if we look back on earlier today, we had formulas for A, B, and C, right? And so we have these formulas. So A is equal to FA, B is equal to 4 FE minus 3 FA minus FC divided by 2T. Okay, let me circle it again. Okay. So now that we have updated values for FA, FE, and FC, we can update these formulas. Right? Unfortunately, it's not like that. And so you're going to hear me say that a lot. So unfortunately, we have to do more work, or it gets more complicated. Okay. The reason we can't use these formulas after we update the surrogate is that this basically assumes that our first value of x is 0, and that each point after that is equally spaced. Okay. So we cannot use these after we update the surrogate. We can't use those formulas, but I do have new formulas. So that's the good news. Okay. The bad news is that these formulas are incredibly long, and you will probably feel a mixture of either sadness and anger at seeing these formulas, And you can feel free to direct them at me, and I will totally okay with that. Those formulas are kind of ridiculous. But these are the formulas that that you showed your friends in humanities today. That we're doing real shit here in engineering. Okay, so let's do the formula for A first. So this is probably the biggest travesty because our formula for A used to be so simple. But now it's not. And yes, there is a fraction involved. We have to all divide this by something. Okay, well, that's the formula for A. So you take FA times XB times XC times the difference of XC minus XB. Okay. Plus the kind of the same thing for FB. So there's a pattern to this, and so once you kind of see the pattern, it you can kind of almost start to fill in the rest of the formula yourself. Okay. Okay. So that's the formula for A. Here's the formula for B. So A is the longest one, thank you. They're all kind of very non-different people. And one thing you'll notice too is that for all these formulas for A, B, and C, the denominator is the same for every single one. So once you compute the denominator once, you can use that for all. Let me box these. Okay, so that's the formula for B. So slightly shorter because we have the squares in there. Okay. And finally, we have the equation for C. We have a minus sign at the end. But don't forget the minus sign on C. That's probably one of the most often forgotten minus signs. If you get the sign wrong for C, then it doesn't quite. Okay. So these formulas actually will work in our original situation too. It's just that when you can assume that XA is equal to 0, XB is equal to T, and XC is equal to 2T, then this just kind of simplifies the model on its own. So these right here are kind of the generic formulas for A, B, and C. Okay. All right. So I know some probably this takes a while to kind of write down. So let me pause here. Are there any questions on this so far? Yeah.
Is this derived from like the system of equations?
It is, yeah. And so if you were to solve that system of equations symbolically, this is the solution.
This will work for all cases, right?
Exactly, yeah, this will work for all cases.
For the second round.
Yes. Yeah, so if you don't want to memorize too many formulas, or you don't want to keep track of, this will work for everything. And so this will even work for the first iteration as well. And so you can just use this. So what I usually do is I set up a macro either on MATLAB script, or I set up it on a calculator for these functions. And you can just kind of plug in the values. So yeah, that's definitely something.
Will the old equations work for cases 2 and 3 still? Or do you gotta use them?
You got to use these ones because those old equations assume that xb and xc are equally spaced apart. But if you're updating one of them to xmin, then you kind of break that. Okay, all right. So let's go ahead and plug these in. So I'm not going to subject you to more for here. So let's just say that we plug these in, and we get these new values. We get a value of A is equal to 288. B is minus 417. C is equal to 125.3. So luckily, once you've kind of done all this hard work, the formula for xmin is still the same. So xmin is still going to be minus b divided by 2c. Okay. And so if you plug in for that, with these numbers here, we get xmin is equal to 1.661. All right, if you compare this to our old value for xmin, or our old, I would say maybe guess for xmin, which is 1.135, you can see here that this is a vast, or it's a big change, right? It's a big change from what it was before. In fact, it's maybe about 50, almost 50% more than it was before. Which kind of reflects the fact that our old surrogate was not very good. So the fact that our new estimate for xmin is so different should kind of reflect that fact. Okay, so let's evaluate this. So let's see how good this is. And so remember, the way that we're going to do this is we're going to evaluate h of xmin. So we're going to evaluate a surrogate function at xmin, as well as our original objective function, f of xmin. Okay. And so remember h of x here is a plus bx plus cx squared. Okay. We have new values for a, b, and c. And so this is equal to 288 minus 417x plus 125.3x squared. Okay. Remember to update your surrogate, right? And so don't use your old surrogate function, use the new one with the new values. Okay. And so if you evaluate this at xmin, so you evaluate this at 1.661, what we get from this is a minus 59.7. Okay. If we evaluate our original objective function f at xmin, what we get from here is a minus 38. Okay. So we're a lot better. So this is a lot better than where we were before. We're not quite there yet, so we're actually going to go through one iteration. But you can see that we're at least moving in the right direction. I used to have a math teacher in high school. Maybe I've told this. Some of you may have heard this before the story, but that was his catchphrase. He said, "This is better." So if you go around And maybe I did bad on a homework one day, and he'll come around, I'll do better. He'd be like, Justin, this is better. And then it kind of just became a running joke. So everyone's, but this is better, that's better. So yeah, it sounds really lame when I'm telling it, but if you experience it, it's a lot better. I feel like there's a lot of things in life that are really like that. Okay, so let's check. Let's check the error. So once again, let's do h of x min minus f of x min f of x min. All right, so we do that for this case. What we get is 0.556. So much better. So before we were at 3.8, which is really far off, but we're not quite there. And so what we want is we want this to be less than 0.1. So we're going to do one more iteration. So we're going to refine the surrogate one more time, and hopefully that's going to be enough to get us to a good approximation. Okay. So this is going to be iteration 3. So our first iteration was kind of our initial guess, right? That's when we were just using the steps. Our second iteration was when we refined the surrogate once. That's what we just completed. So this is iteration 3. Okay. So I'm going to go fairly quickly on this just because it's mostly kind of a repeat of before, but I did want to write it all down just so that you have it complete in minutes. Okay, so once again, let's go ahead and write down x min and t. So our t is still the same. So t is always the same throughout all this plot. Okay, so our x min from the previous step was 1.661. We compare that to t. You can see here that x min is less than t. We have f of x min from the previous step. This was minus 38.37. If we compare that to our current value for fb, which is 43, we can see from these numbers here that f of x min is greater than fb. Okay, and so if you look at these two pieces of information here, we can see that we are in case 4. Okay, so actually the exact same cases will be from the last iteration as well. So let's go ahead and refine the surrogate. And so if you recall, what we do from here is we set fa equal to f of x min. By the way, it is possible to get the same case over and over again, because even though it seems like you're doing the same case, your value for x min and f of x min are updating every iteration. That's totally fine to get the same case. Okay, so f of our fa in this case is going to be minus 38.7. Xa is now going to be x min. That's going to be 1.661. But according to this case here, we leave FB and FC the same. FB same, FC same, XB same. XC is same as well. Okay, so the only ones that we're updating is XA. Okay. So now that we have these, we can recompute A, B, and C. So I'm not going to write down those massive formulas again, but you can imagine that we're using these formulas again here. Okay. And so if you compute those, we get A is equal to 480.2. B is equal to minus 560.94. and C is equal to 149.5. Okay. Okay. And so if we recompute x min from this, x min is just minus b over 2c. And so what we get is 1.876. And then once again, now that we have our estimate for x min, let's go ahead and check convergence. And so let's evaluate both the surrogate function and the original objective function at x min. Okay. So we're going to get h of x min and f of x min. Okay. H of x min in this case is a minus 45.29. And f of x min in this case is minus 42.30. So this is great. These look really, really close. And so we should hopefully be converged at this. Okay. So let's go ahead and check our convergence criteria. So we have absolute value of h of x min minus f of x min divided by f of x min. Okay. If we compute this is 0.071. We check to see if that's less than 0.1. Right, in fact that it is, right? And so we've reached convergence, and so since our surrogate function has converged, what we say is that the minimum of this function is 1.876. So about 1.5 lectures later, we completed one example of quadratic interpolation. All right. So I will say, this is kind of speaking personally. This is not my favorite. This is not my favorite method. In theory, it seems to work great because surrogate functions is something that's used actually quite a lot in applied math. And so you would think it would work really well here in optimization, and it does. It does work really well. There's just a lot of steps to it in a lot of different cases. Okay, and so I do have a code. That implements quadratic interpolation, but it is quite long. So there's so many different cases and so many different things you have to check for. And so I'm going to hold off showing you that code for now, just because I do want to cover a little bit of direct root methods today. But just know that there is an example for it. Maybe we'll do it next week. All right. Any questions on this? Are we ended? Yeah.
So to verify for the third iteration, when you're checking which case it is, FB, you're using the updated FB.
Yes, using the FB from the previous step. So in this case, because we actually never updated FB in iteration 2, it ends up being the original FB. But then if you did update FB in the previous step, you're going to use the update. Yeah. Good question. Okay. All right, and so for the last 10 minutes today, I did want to introduce the last kind of class of methods that are the last class of 1D methods, which are called direct root methods. Okay. And so let me let's before we kind of step into this, let's take a step back. And so remember the whole reason we're kind of doing these very complicated algorithms is that we're almost kind of approaching these problems with almost like kind of one arm tied behind our back relative to where we are, right? And so remember, the whole point of using a nonlinear programming method is that you're not able to access, for whatever reason, you're not able to access the derivative of the objective. Okay. And so in a lot of ways, these methods are a big departure from what we understand as kind of classical methods. Okay? And so we want to find the minimum of these functions, without using any derivative. Because traditionally, if you have a function, if you take its derivative, you set it equal to 0, that'll tell you where the maximum is. Okay, but we're doing this without that information. That's kind of why we have kind of these very kind of complicated, very complex algorithms to do this. Okay. And so for direct root methods, we're going to loosen this up a little bit. Okay, and so direct root methods actually, kind of go back to our classical methods. So in the same way, direct root methods try to find the root of the derivative. And so direct root methods, we're again kind of taking the derivative. We're not actually going to take the derivative. We're going to try to find the roots of the derivative without kind of really taking the derivative. So that kind of makes sense. So that's kind of how we got the name for direct roots. And so we're basically directly trying to find the root of the derivative of a function. Let me make one more point because I did want to end a little bit early today to give you guys a chance to take your exams. Okay. And so I want to kind of make a distinction between taking the derivative of function, that's one thing, and finding the roots of the derivative as another thing. Okay. Because sometimes we may have situations where we can actually take the derivative of the function. And so that function itself we can take the derivative of it. But finding the roots of that derivative is actually the difficult. And when I say roots, what I mean are the locations or the values of x where the derivative is 0. So let me give you an example. So we're going to do this example next time. So let's say that we have our function that looks like this. We have f of x. In fact, this is one of your homework problems as well. Except I don't have you solve this problem using direct root. I have you do it with these other methods. So f of x is equal to 0.65 minus 0.75 divided by 1 plus x squared minus 0.65 x arctangent or tan inverse of 1 over x. So it's a freaking mess. So, but you know, because everything here are kind of known functions, they're quadratics or they're in this case we have arc-trig terms as well. We can take the derivative of this, but you know, after you take the derivative, you know, setting it equal to 0 and solving for x, that's actually the challenging. Okay, and so direct root methods kind of work in kind of this kind of niche where you know where you can maybe you can take the derivative, but you can't find the roots kind of at least in the traditional sense. And so you can do it. You can then find it in a different way using an iterative approach. And so this is going to lead us to actually a quite famous method, and a method that has application way beyond optimization. And so this is called the Newton-Raphson method. Newton-Raphson is used all over kind of applied math and computational physics, computational engineering. It's used for a lot of different things. And so, you know, the direct root methods, you know, it's a little bit of an outlier when you put it next to the other nonlinear programming methods, because it does actually require us to take the derivative. But the Newton-Raphson is just kind of so important for just kind of computational math in general. You know, the fact that we get so close to it, and if I don't cover it, it's almost a travesty. So that's kind of why I'm, you know, that's why I'm kind of covering it. But there's also a way to do Newton-Raphson without taking the derivatives as well, and so that's called quasi-Newton-Raphson, which we're going to go over next. Okay. All right. Any final questions on this before we wrap it up for today? Okay, all right, so I have your midterm exams here. Let me go ahead and bring it over here just so you can pick it up. And so if you weren't here at the beginning of class, the average on the midterm was about 40 out of 50, so you guys did really well. And so go ahead and pick it up, take a look. I tried to grade them pretty quickly, so the comments are a little bit light. And so if you have any questions on kind of why I'm marking down the way I did, then you know, feel free to let me know. All right, so thank you guys for coming today. You know, hope you guys enjoy the rest of the weekend. I will see you guys on Tuesday. Bye. Yeah. Yeah. You can take it. Oh, yeah. Let's just an example, like what one day here with yeah, so for that example, you're right. You didn't have to go through the way because yeah, you can take the derivative of that. But all of these methods are for cases where you can't. The example of doing after ones are can actually take the derivative. Just like, yeah, kind of you sharing on exactly. Okay. Okay. It's also so you can verify after that what you actually
So finding that effects maybe probably
yeah. Okay. Yeah, so it'll make I think it'll really kind of click once we talk about the final project. So I'm working on that right now. And so for the final project, you actually won't be able to finish it's literally possible. Because the objective function you're going to obtain it actually from basically a finite element. You're going to run a finite element simulation, you're going to get the results, and that's going to be part of your study. Because you're using FEA, you can't really take the derivatives of an FEA simulation. Yeah. And so that's where this method comes. Oh, okay.
For the, driveway? Do you get that later, or?
It's gonna be an extra component of the final section.
Oh, okay.
So basically, so the final component right now for the undergrad is two components. So there's an easy problem, there is a hard problem, and for the graduates, the graduate project is going to be just an extra.
Okay. It's a good. Probably good.